Imagine this. You're at a window, you look outside, and you happen to observe that it's quite windy today. Now, based on all the knowledge that you've accumulated over the years about the weather conditions in your locality, you sort of infer that it's more likely to be rainy tomorrow than to be sunny tomorrow. Again, you know this because of all the weather time series data that you've collected and observed over the years. How do we model data like this?
Let's start by making the types of weather the states in the model. For simplicity, let's assume that there are only 3 types of weather: sunny, windy, and rainy. So if the current weather is windy, then there's a 0.6 probability for the next day being rainy, a 0.3 probability for the next day continuing to be windy, and a 0.1 probability for the next day being sunny. Similarly, the probabilities of the next day's weather, depending on whether the current day is rainy or whether it's sunny, are these. Such models are referred to as Markov models. Now, there are a few other properties that they have to satisfy, which I will go into very shortly. But before that, what is a Markov chain? A Markov chain is the simplest possible Markov model. In a Markov chain, all the states are observable and they're all connected like a chain.
Coming back to the Markov property, let's think of it like this. Let's say that you're responsible for accounting for the books in a library. During the week, new books may be coming in, a few books may get borrowed, and it's your responsibility at the end of the week to account for all of this. Now, in order to do this, you need last week's information. The emphasis is you need only last week's information. You don't need any data before that, because all the previous data is anyways captured in last week. That's essentially what the Markov property is.
All the transition probabilities from the Markov model can actually be taken out and represented in the form of a matrix. This matrix is referred to as the transition probability matrix. This is nice because we can actually handle the values now. So each entry ij corresponds to the transition probability of state j moving to state I, not the other way around. So for example, entry 1,3 corresponds to rainy state moving to sunny state. Another thing is that all the column vectors add up to 1. This is because one of the weathers has to happen the next day. Okay, now that we have our probability matrix, let's represent the Markov property mathematically. It's quite simple, really. Let's represent our current state probabilities with a column vector vi, and it's currently 0, 1, 0 because we know that it's windy. So the next state probabilities can be calculated simply by multiplying the current state probabilities with the probability transition matrix.
Now that we know a few things about Markov models, we can use them to answer questions like, given a certain state, what sequence of states must have led up to it? Or something like, what would the weather be next Wednesday?
In fact, the second question can be easily solved by simply repeatedly applying the Markov property. But I think a more interesting question to consider is whether the Markov model will stabilize over time. That is, will V times M give back V? The short answer is mostly yes. Over here, we can transform the equation by first bringing the V's to one side. And we can see that this equation is similar to the eigenvalues equation, where lambda is 1. So basically what we're trying to do is find the eigenvector whose eigenvalue is 1. And solving for this using linear algebra methods gives us the stable state vector.
Now, coming back to the Markov models that don't stabilize, there's actually a theorem for this known as the steady state theorem. And this theorem states that if a Markov model is irreducible and aperiodic, only then it converges.
An irreducible Markov model is one in which every state is reachable to every other state. So this example is not irreducible. In a periodic Markov model, there are certain states that can be only reached periodically. In this example, the period is 2. And obviously, if a Markov model is not periodic, then it is called aperiodic.
So, to conclude, Markov models are pretty effective in modeling uncertain environments where the probabilities aren't direct. Now, they also have an extension known as hidden Markov models. So, hidden Markov models basically contain more layers in them used to represent more complicated relationships. Hidden Markov models are used pretty extensively in NLP. With that, thank you so much for watching. I hope it was helpful, and I will see you next time.